Hi everyone, my name is Raksha and this is my Physics 2 lab report for Lab 5 on magnetic braking with Faraday. So the goal of this lab is to observe the interaction between a falling magnet and an aluminum foil tube to gain a better understanding of Faraday's law. The fundamental physics principles that we'll be applying are, as I said, Faraday's law, as well as Lenz's, Biot-Savart, and Newton's law. And on the left, on the top, we have Faraday's law, as well as mentioning that the minus sign is because of Lenz's law. And then on the bottom left, we have the Biot-Savart law. And a quick summary and glimpse into our results. So for our lab, for a real-life lab experiment, we got a falling time of 2.66 seconds. In our computational model, we got 2.852 seconds. And in this lab report, I'll be walking you through how I got each of these results. So to start off with experiment results, I performed a total of 5 trials and then found the average result of the 5 trials to be a falling time of 2.66 seconds. Moving on to our coding. So starting off with our physical constants and defining them as we usually do. So we have our acceleration due to gravity, resistance, and our u naught over 4 pi. And then setting our initial conditions for the lab. So starting with the geometry of the tube with the length of the tube, the width of the foil, and the radius of the tube. And then the properties of the magnet, such as its mass, and then the magnitude of its magnetic dipole moment. Next, moving on to our functions, we have 2 main functions in this lab code. So our first function is to calculate the magnetic field of the Maurer magnet, and the formula we use for that in this code is shown on line 85. And then our second function is to calculate the magnetic flux, and the formulas for that are in lines 100 and 101. Then we need to calculate the forces. So first we calculate the gravitational force on the magnet, and then we calculate the magnetic force from the tube on the magnet. And then later on we add the magnetic and gravitational force to find the net force on the magnet. And then finally we have our velocity and position formulas in lines 169 and 170. And those are the Newton's second and third laws, which I mentioned earlier on. And then once we run that program, we get an output of as shown. On the left is the visual representation. So on the top is when it's earlier on in the code, and then in the bottom is, as you can see, the magnetic rings are at the end. So that's when the program has stopped running and the magnet has finished falling down. On the right, we have the graph shown on the velocity versus time, and it also shows the time for it to fall is 2.852 seconds. And for on the left, the rings, the blue and the red rings, show and represent the current in different directions, one of them going clockwise and the other anti-clockwise. And also remember the current is opposite to the flux. And then the black tube just represents the foil tube. And then comparing our results from our real-life experiment on the left to our computational model on the right, our real life was 2.66 seconds and our computational model was 2.852 seconds. So pretty close, but our real life is slightly slower in falling time, and this difference is due to the computational model not considering error resistance, as well as the possibility of human error occurring when I did the real life experiment and carried it out. So answering the checkpoint question, so the first one is why can't we use a Ferris tube like a steel pipe? And this is because Ferris tubes are usually magnetic, and so if we used a Ferris tube, it would affect the magnetic field of the magnet, and that would result in less accurate results for experiment. And then the second checkpoint question of what happens to the magnet. So the magnet slows down on its way down the tube because of the increased resistance caused by the magnetic field from the magnet inside the tube. And in free space, there isn't any resistance, so the magnet would fall down much faster. And that's pretty much it for my lab. As you can see, we fulfilled our goal of observing the interaction to gain a better understanding of Faraday's law, and we applied our fundamental physics principles in our real life as well as mainly our coding. And now you know how I got my results for both the real life experiment and computational model. Thank you.